Section 22 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology, Chapter 12, Part 1. Physiography. The topographical features of the earth, the mountains, plains, and river valleys, present a striking appearance to even the most casual observer, and the question as to the cause of their present arrangement is one that naturally arises. It has been suggested that this subject treated from the geological side should be called geomorphogeny, since the geologist makes use of the topography to determine the nature of the changes, while the physical geographer employs the conception of changes to explain the topography. It will be seen immediately how the two subjects interlock, but none the less there is a quite different principle involved. The questions involved in geomorphogeny, then, are those of aggradation, or the elevation of the land, and diastrophism, the removal of land in one place for the purpose of building it up in another. A third class of factors, which, however, are passive rather than active, namely, the character, arrangement, and attitude of the rock masses. A partially degraded region in which the rocks are homogeneous will have a very different kind of relief from one in which the rocks are heterogeneous and differ materially in their powers of resistance to the denuding agents. The topography of any region is the resultant of the very complex interaction of many different kinds of factors, and is subject to continual change according to definite laws. Suppose, in the first instance, a region newly upheaved from beneath the sea into dry land. The topography of such an area will be constructional, due entirely to the processes of diastrophism and accumulation, and characterized by the absence of a highly developed system of drainage by streams. The coastal plain of the middle and southern Atlantic states is an example of such topography, but slightly modified. Next, the processes of denudation begin their work upon the region. The sea attacks the coastline by cutting it back in one place and building it out in another, until a condition of equilibrium is attained. Rivers are established, adjusting themselves to the structure of the underlying rocks and cutting deep, trench-like valleys, while the atmospheric agencies widen out the valleys, slowly wearing down and washing away the sides and tops of the hills. The details of the cycle of topographical development, which is essential in geomorphological reasoning, says Scott, differ widely under different climatic conditions. If we take the successive stages as they are developed in a pluvial climate, with all basins filled, abundant rivers running to the sea, and the snows of winter melting in summer, to constitute the normal cycle, we shall find that the arid cycle of desert climates deviates from the normal in very important ways. Assume the elevation of a large area with more or less of deformation. The drainage will be consequent on the newly formed slopes, and the lowest part of each basin will form the local base level, for the streams of each basin of deformation are confined to the basin and die away in the floor without uniting into a permanent trunk system. In the youth of the cycle, the highlands are slowly eroded, and deposition takes place on the slopes and floor of each basin, diminishing the relief and raising the local base level, a strong contrast to the corresponding stage of the normal cycle, in which relief is increased by the excavation of stream valleys. Even in arid regions, however, valleys are cut on the highland slopes, while the basin floor is made nearly level by deposition. This stage is exemplified by the Great Basin and its mountains. Water is the chief agent of erosion and deposition during the period of youth, but the wind is also important in eroding the bare rocks and in distributing the finer waste, part of which it carries outside the arid region altogether. Extremely slow as this process of complete removal of the finer debris by the wind undoubtedly is, yet it is the only agency which actually lowers the average altitude of the region, for no water flows out of the area we are considering. Maturity of development is attained by the connection of the separate initial basins into a continuous whole. erosion of the highlands and deposition on the basin floors may result in the formation of a continuous slope from a higher basin to a lower one, so that, even in the absence of any permanent stream connecting the two, the rain will wash material to the lower basin and a new and lower base level will be established for the higher one, while the lower basin floor will be built up by the transfer to it of the waste accumulated in that which lies at the higher level. As the coalescence of basins and the integration of stream systems progresses, says W. M. Davis, the changes of the local base levels will be fewer and slower, and the obliteration of the uplands, the development of graded Piedmont slopes, and the aggradation of the chief basins will be more and more extensive. In maturity, the relative efficiency of the eroding agents is not the same as in the earlier stages. The wasting away of the highlands diminishes the scanty rainfall, and the quantity and efficiency of the water decrease with the diminution of relief. But the activity of the wind is not affected, and hence its relative importance is increased. The period of old age, continues Scott, begins with the breaking up of the unified drainage system through the excavation of wind-made hollows in the softer rocks, a process unlike anything which we have found in pluvial climates, where a drainage system once established is not disintegrated during the progress of a normal cycle. If the desert were strictly rainless and erosion carried on by the wind alone, there would apparently be no limit to the excavation of such hollows, but no such instance is known, and the occasional heavy rains suffice to counteract it by filling up the hollows, but the drainage system is effectively disintegrated, and the waste, which in the stage of maturity gathered on the lower parts of the region, is washed about irregularly. The surface worn down by the wind may have no slope in any particular direction, for the wind has no base level and is not affected by the inclination of the ground, but this surface may be reduced to an essential plain-like character. Harder masses of rock, which have successively resisted wear, may rise above the plain as residual mountains, just as they sometimes do in the peneplain of the normal cycle. What has been aptly termed land sculpture, by which is meant the bizarre shapes that rocks assume when acted upon by physical agencies, is due to the effect of varying gradations of hardness in the rocks. When a peneplain or plain of marine denudation is lifted high above sea level, without folding or steep tilting of the strata, streams are soon established upon the new land and proceed to cut deep trenches across the plateau. If the surface layers resist weathering, the plateau will be gradually dissected into flat-topped mesas and table mountains, which in the progress of denudation are converted into pyramidal shapes, while if the whole mass of rocks be easily destructible, they weather down into dome-shaped and rounded hills. The bad lands are carved out of soft and scarcely inundated rocks, but firm rocks of climates of similar aridity give rise to many vertical-sided mesas, as is so notably the case in the sandstones of New Mexico. The Uinta Mountains in northern Utah are formed by a great anticlinal arch, so broad and gently curved that in a given section the strata appear almost horizontal. Out of these immensely thick and nearly level masses, the subaerial denuding agencies have carved an infinite and most picturesque variety of peaks, pinnacles, columns, and amphitheaters, while the streams have cut profound and gloomy canyons. The Grand Canyon of the Colorado is regarded as the most impressive example of this kind. Inclined or tilted strata give rise to a different class of topographical forms. If, as is generally the case, harder and softer strata alternate, the latter will be swept away more rapidly than the former, which are left standing as ridges or cliffs. As the inclination departs from vertical, the more unequal do the two slopes of each ridge become, the longer and gentler one being in the direction of the dip. Ridges and valleys of this class are beautifully exemplified in the Appalachian Mountains. At Kittatinny Mountain, through which the Delaware River has cut the famous Water Gap, the crest of the ridge is formed by very hard and indestructible sandstones and conglomerates, while the broad valley above and below the gap is in slates or other destructible rock. Where, however, the structure of a topography is tectonic in its character, where the strata are folded, ridges and valleys are necessitated, the ridges by anticlines and the valleys by synclines. If the folding be of moderate degree, so as to produce undulations of sweeping and gentle curves, the tendency of denudation is to reverse the original topography and convert the anticlines into valleys and the synclines into ridges. This apparently paradoxical result is found, when examined, to be natural and simple enough. The crests of newly formed anticlines have been subjected to tensile stresses which open the joints in the strata and render them very easy prey to the denuding agents. The surface of the synclines, on the contrary, has been tightly compressed, and their joints are closed by crowding. Volcanic topography is primarily constructive. The cones vary in form and height in accordance with the amount and character of the material of which they are composed, and the nature of the eruptions. Cones are first furrowed with ravines and valleys, and then gradually degraded into rocks or into low hills of volcanic agglomerate. The infinite variety of combinations of soft tuffs, loose masses of scoriae and ash, hard sheets, streams, pipes, and dikes of lava give rise to the manifold forms of volcanic mountains and islands in the course of denudation, the harder elements resisting longer and standing in relief. The Adirondack Mountains display a topography which is strongly dominated by streams of faults. Their general character is thus clearly described by J.F.O. Kemp. The Adirondack region is mountainous in its eastern half and has its highest peaks near its center, but on the west the mountains disappear and the area becomes a plateau ranging from 2,000 feet above tide gradually downward to the west until it is but slightly higher than Lake Ontario and the St. Lawrence. The mountains are arranged in visible northeast and southwest lines, and are often very steep, if not positively precipitous, in the portions that look to the southeast or northwest. There are also other steep faces nearly at right angles with the above, but they are less pronounced. These features are due to three intersecting systems of faults, the principal one of which is northeast and southwest, and determines the general trend of the mountains. The second system, which trends northeast at right angles to the first, is less important and acts chiefly in cutting the ridges into separate blocks. The third series, with north and south trends, is quite subordinate in its effects. Faults frequently determine the location of valleys. The lower Hudson flows in a fault valley of which the Palisades form the scarp, and in the Adirondacks the drainage is so largely along intersecting fault lines that its regularity is very striking and has occasioned the descriptive term of lattice drainage. Brigham. The zigzag course of the Au Sable Chasm is determined partly by faults and partly by joints. The valley of the Rhine above Strasburg is a great trough fault included between the Black Forest highlands on the east and the Vosges Mountains on the west. The most remarkable known instance of trough faulting is the great Rift Valley of eastern Africa. The main valley continues northward from Lake Nyassa and contains Lake Rudolph and several smaller lakes, passing between the plateaus of Abyssinia and Somaliland. It extends to the Red Sea, which is itself regarded as being but a very deep part of the same great downthrow, inundated by the sea. At the northern end of the Great Sea, the Gulf of Aqaba, on the east side of the Sinai Peninsula, is an extension of the trough which, growing shallower, rises to the land and keeps its northerly direction for a long distance. Growing deeper again, it becomes the basin of the Dead Sea, the surface of which is 1,300 feet below sea level, and the valley of the Jordan, and north of that the valley of the Orontes, reaching nearly to Antioch. According to Seuss, this is not an erosion valley, but a tectonic depression. If this interpretation is correct, this vast dislocation extends through 50 degrees of latitude and is one of the most striking structural features of the earth's surface. A river has its stages of development, youth, maturity, and old age, just as has a land surface, each stage displaying its characteristic marks. In a newly upheaved or newly folded land, the streams are determined entirely by the slopes of the new surface and are called consequent streams. As the river system becomes somewhat older, the stream channels are deepened, the larger ones being cut down to base level, and if the region be one of considerable elevation, deep gorges and canyons are excavated. A mature river system is characterized by the complete development of its tributaries and drainage, so that every part of its basin is reached by the ramifying channels. Valley floors are broadened and deposition begins upon them, and the streams, reaching a condition of equilibrium between erosion and deposition, are said to be graded. The final stages of river development are reached when the base level is attained and the drainage basin reduced to a peneplain by the combined action of the streams and weathering. As a river system approaches maturity, it will increase the number of its branches, and those branches which were not at all represented in the youthful stages of the system and are opened out along lines of yielding rocks are called subsequent. However the streams of a district may have been established in the first instance, whether they were consequent, antecedent, or superimposed, they are liable to changes more or less profound and far-reaching. The upstream extension of branches and the shifting of divides result in the capture of streams, or parts of such, by others more favorably situated, one master stream gradually absorbing many smaller ones which had originally been independent. Figure 30 shows two stages in the evolution of a river system. Figure 31 represents the first stage, in which several transverse streams, A, C, E, F, G, are breaching the escarpments indicated by the shaded lines. Of these streams, C carries the most water and will therefore deepen its gorges through the hard ridges more rapidly than the others and give its tributaries the advantage of the greater fall. In the second stage, C has captured the upper courses of all the other streams except G, which has not yet been reached. The branch 1 has captured A, beheading it, diverting the portion A double prime and reversing the portion A prime. Similarly, M has captured and divided E. N has done the same with B and P with D, while G must eventually suffer the same fate. Wind gaps will be left in the ridges where the captured streams once crossed them. End of chapter 12, part 1.